Okay, so yeah, me again. So I'm going to talk about transformers, symbolic models, but today we're more going to look at easier problems and try to understand what they do and what we can learn about the way they learn and what they do. So there's a couple of questions for transformers in general and transformers doing math. So there's a question which is, do they really learn? Do they really learn the math they do? Or are they just cheating, learning shortcuts, parroting, as a famous paper said, statistical patterns? There's a second problem, what about the failures? Because it's been saying that those models hallucinate, they confabulate, they create crazy solutions. Are the failures predictable? Are they principled? Or are they totally random? Another question is, are they really black box? Or can you explain the prediction? And finally, we've talked about that yesterday, what about the training data? We see that the training distribution, we generate the training distribution, what's the impact of this generation? We spoke about it this morning again, about the Grobner basis, it's very important. So I'm going to show you a number of papers. So this one is a paper from 2021 called Linear Algebra with Transformers. So it's sort of known that transformers are pretty bad at mathematics, at computation. They're very bad at addition, multiplication. You need to train them a lot. So here I try to say, okay, let's not do exact computation, but approximate calculation, and let's try to go for matrix computation. So the idea is that it's very easy to transform a matrix into a sequence. You just enumerate the coefficient, line after line, so it's very easy. So I look at 9 problems of increasing difficulty. So transposition, addition of 2 matrices, dot products, so a matrix times a vector, matrix products, and then eigenvalues, eigendecomposition when you want the values and the vectors, singular value decomposition, and matrix inversion. Okay, so how do you represent matrices? Well, matrices are a sequence of n times n entry that you can tokenize as triplets. So sign, mantissa, exponent. So every entry of the matrix is a sign, a mantissa. So the mantissa has 3 significant digits. That was a design choice. It could have been 4. So they're an integer between 100 and 999. The sign is plus and minus, and I got 2 exponents. I got 1 exponent between minus 100 plus 100. Why the exponent notation, the floating point notation? Because then I have a larger dynamic range at the price of a little less precision. So the matrices are randomly generated with uniformly sampled coefficient between minus 10 and 10. So basically they are, that ensemble known as Wigner matrices. The solutions are computed with NumPy. There's no problem with generating anything here because these are solved problems. And of course, I'm predicting a matrix or I'm predicting a vector. So, and everything is floating point, so there's absolutely no reason to want exact precision. So precision is measured as a closeness. So basically, I'm considering everything as big vectors. So it's Frobenius norm, if you like, but L1. And I'll explain why it's L1, because L2 tends to privilege small or large coefficients. So I want a relative error, a maximal relative error, or relative absolute error, of less than 5%, or sometimes less than that. Okay, so this is it. So if you train model, I won't, get you through the training the transformer representing all that. But the main results were quite interesting. So the first thing is that the basic linear algebra is learned with very small models. A 1-layer transformer can learn to transpose with 100% accuracy matrice up to 30 times 30. Well, transposition is not difficult, right? But it works. Matrix addition, you get 99 accuracy with matrix up to 20 times 20, or dense matrices with very small transformer. And then for products, matrix vector products, or multiplications. The most interesting part here is the bottom part, because that models could learn to add or multiply seems relatively easy, but that they could calculate eigenvalues just from sequence of elements is a little more surprising. But eigenvalues were fairly easy. I got 100% accuracy, or very close to that, for any matrix between 5,5 and 2020. For 2020, I had to really work for it, and it took weeks, and there were many tricks. But 5,5 to 8,8 was fairly easy to achieve. I could also do eigendecomposition, so close to 100% for 5,5 matrices. 6,6 become more complicated. Eigendecomposition, I mean eigenvalues plus eigenvectors. Okay. SVD became way more difficult than the rest. And matrix inversion, I had 90% accuracy, and we'll see why in a while. So the first thing is that, yeah, surprisingly, the model is very bad at precise calculation, like exact arithmetic on multiplication of large numbers. But matrix calculation, no problem, which is, interesting. So yeah.
What do you mean by 100% accuracy?
So I mean, yeah, accuracy is so I have a test set of a few thousand, usually 10,000 examples that were not seen at training. And I consider that the model correctly predicted, for instance, the eigenvalues, if all the eigenvalues are within 10% within 5% of the correct values. So if everything is within 5% of the correct value, then at that point I'm saying, okay, this is a correct one. So 100% accuracy means all 10,000 test examples were correctly predicted. Yep.
What is the ratio between the test parameter size, for example, 13 times 13 matrices times the number of coefficients, and the number of parameters in your model?
So that's
does your model just store all the results?
So
or it is much more smaller and could not store.
So just to give you an idea, 5 matrices with numbers with three significant digits. You have 25 digits, and you have 1,000 possibilities or something like that for each.
You don't know how much parameter you have in your model?
The model has about 10 million parameters, between 10 million and 100 million, depending on the size. Yep.
How does it scale when you go to
Larger dimensions? So the main problem you have is the length of the sequence. So actually, when I say everything was tokenized with 3 tokens, I have also tricks for you're doing only 1 token. The problem is that if you want to do 30 by 30 or 20 by 20, it's 400 coefficients. If you need 3 tokens, it's 1,200 coefficients. And then it becomes difficult for the model because the sequences are long and the attention mechanism, which is quadratic, suffers. So the learning becomes difficult. One thing I've noted, what? Yeah?
with your model, will you one day be able to handle 100 by 100 matrices?
No. It's impossible to do very large dense matrices. Or rather, I couldn't do very large dense matrices because the sequences are too long. And the transformer, the number of tricks you would have to add to the transformer to do something that NumPy does better, by the way, is probably useless. For very large sparse matrices with a different encoding where you would not encode the zeros, etc., then in that case, probably something would be possible. But here the goal was dense matrices, really.
I have
Yep.
a related question. How does it scale with respect to this 5% precision that you asked? You go to 1%.
Yeah, so that's a very good question. What I observe is that, so I have 3 significant digits. So 0.5% is the best I can have because it's a rounding error, basically. On all my model, if I train for more time, I get closer from 5 to 2 to 1, and it sort of blocks around 0.5. So if I put more compute at it, usually the model improves for almost all problems I've noticed. So this is in the paper. In the paper, I provide the values for all the tolerance. So you can have a look at it. Of course, in some case, like transposition, etc., it's almost exact because you just need to copy the coefficients. So the model is not even cheating. It's doing everything correctly in that case. In all other cases, it sort of scales.
But for instance, 3 by 3 matrices, but then with, let's say, 5 digits.
So I tried 4 digits. 4 digits works exactly the same. You just need more examples because the vocabulary is larger. I didn't try 5 digits, but the thing is that if you have more digits, you will have a larger vocabulary or longer sequences, depending on how you encode them. And for this, you will need more examples to train.
But do you need an exponentially
No.
more examples?
No, it's more or less linear. It's more or less linear in the size of the vocabulary.
100 digits, you would just, but 3 by 3 matrices.
So the problem with the 100 digits is that at one moment, 3 by 3 matrix, 100 digits, I don't know. I don't know. I would need to check that. I don't really know. Yep.
So what is the distribution of the eigenvalues of the set of matrices?
So I'm coming to that.
But I mean, it's not random number.
Yeah. They're Wigner matrices, and the eigenvalues are semicircle. But we'll see, because this is one of the points I want to make. Yep.
So that's something I don't understand. If you have a function that can be approximated well enough by something like a polynomial or a simple function, isn't it expected that the model will just learn an interpolation of that function? For instance, if you have,
Yeah.
I don't know, this coefficient of the product, where it's just the product of some two of the coefficients and
Yeah, the thing is that you have, if you do addition or multiplication of two 5x5 matrices, you have a function with 25 variables. And that take a lot of values. So, the possibility to learn it into a couple of tens of millions of examples is in itself not clear. And again, if you do addition and multiplication, you suffer when you do that with a transformer. So it's not that clear that you could learn.
the task that would be similar to addition and
True.
multiplication on the
True.
big numbers would be
True.
something like learning on small rectangular matrices and
Yeah.
learning to multiply matrices.
Yeah, this is true. This is true. And note also that the matrix coefficients are discretized here. So it's not, I'm not inputting numbers and getting numbers out of it. I'm inputting discrete token and outputting discrete tokens, which is, maybe something different. But I agree. Okay, so the question here, the question I was interested in is, okay, do we learn the math? And so I'm interested, we'll talk about two problems. The eigenvector calculations, okay, so diagonalization, and eigenvalues. So I'm starting with a symmetric matrix M. My model is going to predict a matrix, an orthogonal matrix H and a diagonal, so H and D, such that H M H transpose equals H M H minus 1 equals diagonal D. That's the spectral theorem. But the model doesn't know that. The model only sees triplets MDH and knows to translate M into D and H. So I know from theory that the D's are the eigenvalues, and if I sort them, they're basically unique. I also know from spectral theorem that H will be unitary, in this case orthogonal, because it's symmetric, and that the rows and columns will be orthogonal, 2 by 2 orthogonal, and they will have unit norm. Okay? So it would be cool if I could show that the model learns that. It would show that the model is somehow learning, on its way, just seeing examples, it learns some of the mathematics. So the idea here was say, okay, let's train a model to high accuracy, like 92% accuracy. Once the model is trained, not 100, you don't want 100 because you want to test on the errors, on the failures. And you test it on 100,000 matrices. So basically you're going to have about 8,000 errors. And now you look at the errors. And what I noticed is that in every test case except 6, so in almost all of the 8,000 errors, the eigenvalues are predicted with less than 1% error. So even when the model is wrong, doesn't predict correctly D and H, D is always correct. The eigenvalues are learned. Other point is that in all the eigenvectors they have learned, in almost 99% of them, the columns of H have unit norms. So the failures of the model are sort of explainable. The model predicts you a matrix D, a matrix H. D is usually the correct eigenvalue, and H is not quite an orthogonal matrix, and it fails on the 2 by 2 orthogonality of the columns, and not on all of them, on a few of them in general. So this is something I found quite interesting because, the question is the machine learning some kind of a trick, etc. No, the machine seems to be failing for, learning some of the underlying mathematics. Just like you would say a student has learned something if it, never fails predicting this, if the calculations are always done correctly, you would say the student knows that. I'm claiming that the matrix have sort of learned the properties of diagonalization because it observes them even when the model fails. So there's no such thing as hallucinations here. Yeah?
Another question. If you slightly change the input matrix, so you how are the things going to change? Because that is another kind of thing you
Yeah.
would expect from a continuous or a nice function that happens.
Yeah, that's a good point. I haven't tested that, so it's something. It's something I really should do on this. That's. Yeah, I don't know. But this.
So does this mean that there are ways to compute the eigenvalues or extract the eigenvalues from the coefficients of the matrix without solving any polynomial?
Well, all the model is learning a mapping that does that effectively. I don't know, but it means that the model is doing that. Obviously, it can predict the eigenvalues this way.
Mapping, you have to do matrix multiplication on your GPU.
I would think so. But actually, the eigenvalues are learned faster than matrix multiplication. It takes less time for the model to learn, less examples for the model to learn eigenvalues than matrix multiplication.
You need much larger matrix. When you apply your model on GPU, you do computation with linear algebra in much higher dimension than 5.
Yes, true.
So you could use it directly.
It's quite possible that the model knows that. I don't know what it does. I observe it does it correctly.
So you have no explanation for this?
Sorry?
Do you have an explanation for
Why it does that? No, I just observe this.
That's scary.
It's not scary. I mean, it's absolutely beautiful, don't you think? We are learning the mathematics just from examples. It's so inhuman.
No, it's machine.
Yes, and it's just from example. So let me continue on this. So, these properties of matrices, you could say, okay, the model sees so many examples. So maybe it learns to calculate, and then at the end, like a cherry on the cake, it adds those properties. And by the way, everything. But it's not the case. I try to stop training early. So I train my model, and even instead of waiting until 90% accuracy, I stop at 70% accuracy. So my model is sort of half-trained. And I look at the prediction of the half-trained models, and again, the eigenvalues are correct, and the unit norms are a little less good, but it's still 97%, so pretty good. I also tried on larger matrices. You remember for eigenvalues, 5 does well, 6 does worse. So for 6 matrices, my model is too small. I would need a larger model to do that, but with my small model, I only achieve 43% accuracy. So the model predicts less than half of the correct matrices. But the funny thing is that even at this low level of accuracy, eigenvalues are still correct. So the model has learned eigenvalues before eigenvectors, as it should. I mean, mathematics says that it's an easier problem. So it managed that. And the rows and columns are mostly unitary. Okay, so this is very challenging if you compare it to the usual theory of transformers, because, just a second, because the theory on transformers is that transformers, when they're wrong, they totally hallucinate. There's no hallucination here. Here, when the model is wrong, it's wrong, but it's very close. The apple falls close to the tree, basically. Yep.
I'm not sure I understand. So the fact that the norms are 1 comes from the fact that all the input data you feed has that property.
Yes.
It's not surprising that
Well, the fact.
it's not a mathematical property. It's a convention that you make because you actually can scale an eigenvector.
Yes, this is true. But the thing is that.
So what would be more surprising here is if the orthogonality was check that.
So the orthogonality is not quite, because if I had norms 1 and orthogonality, it would be, it would be perfect. So the orthogonality is partly verified. So I don't have things that are widely, it's not a square, it's sort of skewed. So the things are not perfectly orthogonal, the different coordinates are not perfectly orthogonal, but orthogonality proves to be harder than unit norms. The thing is that it's not that easy for a transformer to be able to notice that all the vectors have unit norms, because there are different coefficients scattered among the same sequence. I'm not giving them, it's not represented as vector, they're just coefficients. So it's interesting to see that the model still predicts that. But I agree with you that you can learn that from the data. Learning the eigenvalues from the data is a bit more complicated. Yeah?
And if you impose this orthogonality relation, does it learn better?
If I impose it, well, yeah. Well, you could impose it in the loss function, but in that case, well, it would make the loss function very complicated. I would expect it would help. I would expect it would help. This would really have to be tested. I wouldn't know how to do it. I have to say my approach to that is never to do mathematics during training. So I'm sort of opposed, you know, in order to understand what the model is doing, I try not to have mathematical information in my loss. My loss is just coarse entropy here. You predict the correct token or not. But that's, yeah, that's a bias on my side. So the other thing is that you can understand the model failures. You know, almost all the failures are due to rows and columns not being quite orthogonal. They're never terribly unorthogonal, but they're close to, but not quite. The eigenvalues, the normal eigenvectors are learned. And actually, you know, you have a factor for determining the orthogonality of a matrix. It's the condition number. And it's very interesting because you can see, if you look at the condition number of H, you can see that the model outcomes is perfectly predicted by the fact that you have a condition number close to 1. Okay, so this sort of justifies, you know, this intuition that it's all about orthogonality, in that case, the condition number.
So you're saying here, just to make, if you like double or triple the number of parameters in your model, like take, I don't know, 500 millions instead of 10 millions, and you give it like a matrix 3 by 3, will it start hallucinating at some point?
No. No, if you have a larger model, usually you will learn faster and better. It's something surprising, but more parameters help learning. It doesn't hinder learning, never. So if you have a larger model, you will learn faster the small matrices, and you will be able to learn larger matrices. At least that's what I tried for these matrices from, you know, 10 million to 1 billion, and I observed that on every single experiment. So I'm quite sure about that. So on the model failures, I had another look. You remember among the things I calculated, there was matrix inversion. And I had a problem with matrix inversion, which is I never was able to do more than 90% accuracy. And I tried larger models, I worked a lot. So in that case, I looked at matrix inversion. And what I noticed is that the matrix correctly predicts, you know, predicts a good approximation of m-1, but the value mp equals identity never holds, because the matrix is badly conditioned. So the thing that was observed here is that the 10% accuracy systematically correspond to badly conditioned matrices in my test set or training set. So I really like this thing because, you know, badly conditioned matrix, it's a problem in inversion, even for NumPy, for everyone. So in the case of inversion, the model fails for a very, very good reason, which is conditioning, which is a numerical reason. And actually, just by calculating the condition number of the input matrix, I can predict almost perfectly whether the model will be right or wrong. The trained model will be right or wrong. So in that case, the errors are totally explainable. Yeah? Okay, so what you see here is that on this, you know, sort of toy examples, you can see that the idea that the model somehow is magical, you know, maybe that's an impression you had yesterday, that the model does something we don't understand, etc. No, actually, on simple problem, you can understand that the machine is doing something mathematically that makes some mathematical sense, or is learning mathematical properties that we know. It's not inventing something crazy. So the takeaways is, curiously, whereas transformers suffer from a large number multiplication, you can learn complex operation like eigen decomposition surprisingly well. For small matrices, yes, but you can do that. So it's a bit surprising. Some of the underlying mathematics seem to be learned, and they fail for mathematical reasons. And the failures seem to be principled and predictable. And this will be a theme of the rest of this presentation. Yeah?
So here's a bit of a provocative question. So these are exactly the same weaknesses that traditional numerical algorithms have. So why do we do machine learning?
So in that case, that was the question all the reviewers asked me on this paper, and it was a hell publishing it. So I'm, of course, not advocating replacing NumPy. This is slower, this is inefficient, this is random, etc. What's interesting here is to understand, so I'm interested in all this presentation in using machine learning to learn problem we know how to solve in order to understand or try to understand what the transformer and the machine learning is doing. Because, you know, if your language model fails at translating from French into English, the only thing you can say is that it failed. If it fails on mathematics, you can leverage the mathematical knowledge, the theoretical knowledge you have to try to understand why the model fails and how the model learns. So the goal of all this is to try to get a better intuition on what works and what doesn't work with transformers, and then to improve the architecture or get to do better AI for science or mathematical discovery. So that's more or less the goal here. The goal is obviously not to, don't try this at home if you need to invert matrices. Yep?
But it would be cool if you could say, okay, I can use machine learning to benefit for the other mission.
Yeah, but in that case, the problem is people ask me, will it scale? And I doubt it will scale because the models are too large and the sequence don't scale well. This is a very well-studied problem. So one thing I can say in favor of this is that a lot of hard problems in science include those kind of applications. So if your model is not able to add or to do matrices or anything, you can doubt it will ever learn, the more complicated tasks you would like. So you can think of it as a proof of concept that this is possible with a transformer. I'm not sure if it's such a good reason. At least that's not why I did the paper. Yeah?
In your matrices, you didn't specify the coefficients that were in your matrices. So you said it would be floating points or integers. But you only give to your model actual data, but what if you give wrong data, that is matrices with, I don't know, integers and floating point mix? That doesn't have sense. Will it still transpose the matrix correctly, the data?
So for transposition, I'm pretty sure yes. For all other operations, I'm sure no. Basically, if it has never seen a negative number, it's not going to invent one for you. But it's like priming yesterday. If it has seen just a few negative numbers, it will usually be enough for it to adapt. So the thing is that the model will not adapt to symbols it's never seen, but it's able to adapt to things, if you give it just a few examples, adapting to new things is possible. Yeah?
So then, does priming help learn to work on larger matrices?
So for larger matrices, so I only have one example that was for the eigenvalues. So if I train 5-5 matrices, I get the eigenvalues quickly. If I train 8-8 matrices, it takes a lot of examples and it doesn't happen all the time, but most of the time I manage. Starting from 9-9, I never could manage except if I increase the number of parameters. But then I tried something. I had a training set which was 5-5, 6-6, 7-7 up to 20-20 in equal parts. And the model ran for almost a month. But 5-5 were learned, and then 6-6, and then 7-7, and then 8-8, and I was very surprised because I went up to 20-20. So it took a very, very long time. So the thing is that if the model sees many different sizes of matrices at the same time, it will learn them in order, but it will be able to learn to calculate the eigenvalues of larger matrices that it seems not to be able to learn if you just have like 10-10 or 12-12. So this is the only, I could manage to do that on the eigenvalues. I couldn't do that for the other things, so I don't exactly know why, but this seems to happen. I then tried another thing more recently, which was trying to embed, right now the embedding of a matrix depends on the size of the matrices. So the 5-5 matrices are embedded like sequence of 75 tokens. The 6-6 like 3 times 108 or something like that. So they're embedded in different dimensional space. And this doesn't help, to learn common. So I try to force everyone to learn on the same size. And I noticed that it doesn't really help the scaling to better thing, but everything is learned 3 times as fast. So there is something about the embedding that would deserve more study, but something seems to happen. It's just not obvious, just adding a few elements. And you need to have all the scales at the same time. If you train on 5-5 and retrain on 6-6, so this is in the paper, you will learn 6-6 faster than 5-5, but when you learn 6-6, you forget 5-5. This is catastrophic for forgetting, and you get that. So if you want to learn 5-5 and 6-6, you can start 5-5 and then add 6-6 and train on the 2, and you'll save a little time. But yeah, you cannot, retrain a model and expect it not to forget what it has learned.
Related to the eigenvalue, so if I train, like a simpler problem, if I train the model with, let's say, a million quadratic equation with real solutions. But I just hide like solutions with no, equations with no solutions. Like I train my model and then I supply something like 1 plus x squared.
Yeah.
So it's gonna provide what? It's gonna provide something which is gonna be completely wrong, right?
I don't know. I could train a model to find the roots of polynomials. It sort of managed to calculate the roots of an integer polynomial, as complex numbers. It does that not very well, but it does it.
It won't invent complex numbers.
No, it won't invent.
So it's gonna give like a simple.
Oh no, the machine doesn't produce concepts. It works with the vocabulary it has already. You have to give it examples of the vocabulary. Okay, let me move a bit. I'm happy of all the questions. Oh, okay, go on.
So you said that the model learns some of the underlying mathematics, but in that case, wouldn't we expect it to be able to generalize slightly? For example, if you train it only on 3x3 matrices, wouldn't you expect it, if it did something, to work also on 3x3 matrices?
So, no. The problem is that the length of the sequence is the problem here. So I think, yes, my experience with 5 and 6 and 7 and 8 shows that it learns from each other. But if the model has never seen, the model only sees examples. If all the examples it have are 25 tokens, there's no way the model will invent what happens with 36 tokens. There's no way out of that. But that's the point of priming. If you just give it a few, then it works. Then it starts working. But you need to provide examples. That's really the limitation of those models that are only trained on data. Okay, so let me show you something else. We talked yesterday about distributions, different training distributions. So in the case of eigenvalues, it's very cool because I have all the random matrix theory that I can use. And so my transformer I show can learn easily the real eigenvalues of symmetric matrices. It just takes a while and it works. My model are trained on symmetric matrices with independent entries, and I know that these guys are Wigner matrices and the eigenvalues are distributed as a semicircle. And the convergence is pretty quick to the semicircle because the eigenvalues are repulsive. So I'm expecting a distribution that is symmetric around 0, that have a variance that depends, on the coefficient variance and matrix dimension. There are formulas for that, and that have a bounded support. So the question is, am I really learning to calculate the eigenvalues of matrices or just the eigenvalues of Wigner matrices? And of course, this is very easy to test. Basically, you could generate a lot of non-Wigner matrices. So how do you do that? You generate a Wigner matrices, if possible, with Gaussian entries so that the eigenvectors will be von Mises distribution, will be in all directions. You do diagonalization. You remove the diagonal and you replace it by a diagonal with the same variance. So you don't want to change the variance here. With the same variance, but with different distribution. And so, having done that, the idea, I wanted to experiment with different distributions. So I start with my semicircle, so my Wigner original thing. I try to have uniformly distributed eigenvalues, so bounded space, symmetric but uniform. And then unbounded Gaussian and Laplace, same variance but fatter tails. And then I try the positive version of it, why not? So absolute semicircle, so you pattern labs in front of it, absolute Laplace, and the Marchenko-Pastur or something similar to that, to have an example of a real life, whatever this means, matrix. So basically, I did that by having the product of two matrices, so building covariance matrices. So this table looks a lot like the one I presented yesterday. So the lines are the training set, and the columns are the test set. So the top line, semicircle, semicircle, is what happens if you train on a set of Wigner matrices and test it, and you get 100%. This is what I told you. But of course, if now you test it on uniform Gaussian and Laplace, the wheels start to go off. It works because there's some duplication between them, but you only at 30% accuracy. And if you go to positive definite matrices, well, you haven't seen one in the training set. The model cannot invent one. So far, the answer is no, it doesn't generalize. But it gets, and of course, if you look at positive definite matrices, so the three top bottom line, you can see that if you train on positive definite matrices, you learn to predict the eigenvalues of positive definite matrices. But the negative eigenvalues of the others, you've never seen one, so it don't happen. So why do you have 5, 4, 4? These are the very, very small number of semicircle matrices that are actually positive definite. So that's why, it sort of works. Yep?
Still on that you get wrong answers. Is there some pattern in these wrong answers, or do these wrong answers still make sense in a way that somehow we don't directly understand, but maybe there is some pattern?
So in this case, what I noticed was that if you do semicircle, if you train on semicircle and test on other things, the model is going to try to observe the semicircle structure of your data. So you will get a zero thing because you will have negative eigenvalues all the time because the model always has seen negative eigenvalue, which is why you have 1 or 5 or 0 on Marchenko and all that. For Gaussian and Laplace, you can see that the eigenvalues that are wrong are the largest one because the semicircle has no tail. So it's the same story as before. It is going to try to adapt to what it has seen during training, which is the semicircle distribution. But the interesting part here are the bottom column, Gaussian and Laplace. Because you see, this is by no means a fatality. You're not doomed not to be able to generalize. If you take the Gaussian and Laplace, so if you train on model on matrices, which are, I don't know what this ensemble mean, but ensembles of matrices with eigenvalues in every direction, but eigenvectors in every direction, by eigenvalues distributed as Gaussian and Laplace, with the same variance, etc. You generalize to uniform Gaussian Laplace, also to semicircle, so it works. And you even can calculate the eigenvalues of positive definite matrices, even though you have none in the training set. And this is extremely surprising because this is very, very long distance generalization. And this suggests that, generalization out of distribution, we saw that a bit with Lyapunov yesterday, is possible if you have the correct training distribution. I have absolutely no explanation for that. I just observe it. But it's something that is very strange because to my knowledge, this is the first time we observe, such a long distance generalization. And this seems to happen in this case if you have some, kind of magical distribution. A funny thing with those guys is that suppose you try larger matrices, 8, 8, and 10, 10 matrices. In that case, after 36 million examples, I don't have enough examples for my small models to learn them. So you see the Wigner matrices on 8, 8, they are 0 even on the Wigner because you didn't have enough examples for the model to start learning. But if you train them on Gaussian and Laplace, you learn Wigner on the Gaussian and Laplace. So these robust distributions are not only robust, they are more efficient in terms of training. They need less data. And, so intuitively, the fact that the eigenvalues are more widely distributed seems to play a role, and maybe it makes sense, I don't know. But obviously, there is something important here, which is sometimes you can get long-distance generalization out of your training distribution, if you are lucky enough to find the right training distribution. So obviously, the problem would be how do you characterize the distribution, and this I don't know. But this is, I think, an important finding. Okay, so the takeaway here is out-of-distribution generalization is possible. And there seem to exist special robust distribution, and we're going to see more of those, that allow for faster learning, that are to some extent problem independent. I didn't show it here, but actually these distributions also perform better when you did eigenvectors, eigenvalues and eigenvectors. So this is a related task, but it's not exactly the same, and it sort of helps. So I don't know why. And the whole question is, could we find a theory of that? If we could have a theory that say, here's the best training distribution, because this is a lot of hope. It says, now you have a problem which is not just generating data to train your model, but generating the right distribution so that your trained model can generalize widely out of your distribution. Yeah? So, okay, let me move forward out of the matrix calculations. And so we know that transformers can learn complex calculation. I showed that yesterday. You can do Lyapunov, you can do eigenvalues, eigenvectors. But it's also known that they struggle on basic arithmetic. And yeah, this is not nice. So for addition, you can manage to perform addition if you add scratch pads. So you show the successive results to train the model. And if you do that with a lot of work, you'll be doing long number addition. But you have to work for it. Multiplication, well, one operand must be small. In ChatGPT, it used to be 3 operand max. Well, at least for one of the 2 elements. Now it's 5. But it's difficult to learn integer multiplication. And if you want complex operation, you know, if you want addition plus multiplication, scalar product, exact things, then everything becomes difficult. There's a couple of papers on that. Yep.
Do you switch in your presentation between these two slides from a specific model done only for matrix multiplication
Yes.
to a generalistic model done for
No.
everything?
No. No, no. All my models are trained on only one task. I'm working one task at a time. I'm not at the idea of having many, many different tasks.
So
And
these sentences apply to a specific model trained only for...
so the ChatGPT is something applied to everything. The teaching arithmetic to small transformer, they train different machine on different problems. And notice the difficulty, so the fact that it's difficult to generalize, you have to work for it, and if you want complex, more complex than just addition and multiplication, just mix and match them. If you train a model on a lot of examples, you really suffer. So I'm going to talk about 3 arithmetic tasks here. So calculating the greatest common divisors of 2 integers. So I take 2 integers randomly taken between 1 and a million, and I want to compute the GCD. You know, does it work, does it not work? You know, you might wonder, because if multiplication is so hard, why we calculate the GCD correctly? But anyway, and the 2 other ones are addition, modular addition, and multiplication modulo P, where P will be prime or not prime. And the idea is that I don't want to be in a finite field, because if I want to do modulo 67, which I will do here, I only have 67 times 67 possible things. So my model is going to overfit. That's the subject of grokking, lots of paper on that, but it's not really interesting. So I take 2 numbers between 1 and a million. I have 10 to the 12 possible entries, so my model is never going to memorize because it will never see all the cases. And I do the addition, and then I do the modulo. Same for multiplication, you know, just to, so this is the operation I'm trying to learn. So the first thing is the greatest common divisor. And the intuition was that, okay, if the model suffers so much with integers, could you do rational numbers? You know, it works for eigenvalues, so maybe rational numbers are easier. So I have A and B between 1 and a million. There are 10 to the 12 possible examples, which means that if I randomly get a test set and a train set, you know, the birthday paradox is done in such a way that I have almost no duplicates, so it's very easy to do. One property, you know, which is due to Cesaro, is that the probability that the GCD AB for 2 random numbers equals k is 1 on k square. Well, something constant on k square, which means that you have 4 times 1 GCD1 and GCD2, 100 times 1 GCD1 and GCD10 on those random sets. And you have about 61% of the random GCD that have the random pairs that have GCD1. Saying that because we're going to see it again. And you know, I got 2 numbers, I need to tokenize them. How do you tokenize integer? Well, as sequence of digits in some base. So the thing I'm going to study is the base. You know, what happens if I represent my numbers in base 2, in base 10, in base 3, in base 1000. Okay, so how do I choose the base? Intuitively, if I have a small base, my sequences are longer, so it's more difficult to learn, but the vocabulary is much smaller because you have very few digits, so it will be easier to memorize, okay? So there's a trade-off here. The other one is prime versus composite. You know, if you have a prime base, then fractions don't simplify, so somehow everything is cleaner. But if you have a composite base, a lot of divisibility rules are easy to learn. In base 10, divisibility by 2, 5, 10, 20, you just look at the last digit, it's very easy, right? In base 31, it doesn't work that way. So the first experiment I did, that's many, many years ago, was, okay, can we learn the greatest common divisor? And let's use a composite base. It looks like, you know, a good idea because divisibility, it's linked to divisibility, will help. And so here you got 2 models and you got the learning curve. So the x-axis is the number of epochs, so the number of times 300,000 examples I've seen. And the other one is the accuracy, so the number of test cases out of 10,000, I think, or 100,000 that were correctly predicted. And I'm using the smallest possible transformer I have, 1 layer, 64 dimension, that's 300,000 parameters. You can't do anything but that on this. But it works. After just 1 epoch, after 300,000 examples, my model achieved 85% accuracy. That's 17 out of 20. It would, you know, the student would get the exam. And after for a couple of million examples, I'm at 95% accuracy. So it looks like the GCD can be learned. Well, it looks like that until you try base 31 and you have the green curve. In base 31, well, you have 61%, and you can guess with me what the 61% means. The model always predicts 1. And nothing is learned. Nothing moves. You can give tens and millions. And it doesn't improve if you try more bases. So here you've got base 30, 6, 10, 2, 3, 31. So we're really learning the GCD? The GCD is not supposed to be dependent on the representation base. So something strange is happening here. So how do you understand that? Well, it's very easy. You could take a very large test set on your trained model, and you're going to have a test set that is organized where you have 100,000 examples, and you have 1,000 pairs of examples, random pairs with GCD1, 1,000 with GCD2, 1,000 with GCD3, etc., from 1 to 100. So what you have in the table, the GCD is the value of the GCD. I give you the 33 first. And I give you the most common prediction of the model and the frequency of the most common prediction. So the first thing you can notice is that for any pair of GCDK, the model only predicts 1 GCD. So if you have 2 pairs of numbers with the same GCD, the model will make the same prediction. Correct or wrong, I don't know, but it will make so the model is able to tell that 2 pairs have the same GCD. That's fun, we cannot do that. For fairly large numbers, without calculating, we can't do that, but the model can do that. If you look at the correct prediction, there in red, you see that the correct predictions are 1, 2, 4, 8, 16, 32, powers of 2. But it goes further. If you look at the incorrect prediction, you can see that all odd numbers are predicted as 1. And even numbers are predicted as the largest power of 2 that divides them. And this works for all the values and all the models I've tried. So what happens? What's the model doing? Well, the model is cheating, it's counting zeros. How do you tell that a number is divisible by 2? Well, it has to have 1 0 in the binary representation at the end. So the model is reading the number of zeros on the right of the operands, making a min, and this is the prediction. And you can see that in that case, if you have the GCD of 12 and 24, the model will say, 2 zeros in 12, 3 zeros in 24, so the GCD is 4. Of course it's wrong, but that's what the model predicts. Sometimes it works. If you try 52 and 68, it works. We're lucky on that one. But the model is wrong, and this explains the prediction. If you look at base 10, you got the exact same pattern. The model always predicts a single value. The correct predictions are 1, 2, 4, 5, 8, 10, 16, 20, 25. The products of small powers of 2 and 5. Why? Because divisibility by 20, for instance, is very easy to judge. You look at the 2 last digits. If it's 0, 20, 40, 60, 80, then divisible it is. If it's not, it's not. So the model is cheating, and you can understand why it's very bad for prime numbers. Because for prime numbers, those easy divisibility rules you never learn. So, yeah. Well, yeah, but the model doesn't learn it, or neither does it learn 9 or 11, you'll notice. And this doesn't work because I think the problem is that divisibility by 2, 5, 20, you just have 2 tokens to look at. You just look at the tokens, and the attention is meant for that. 3, 9, 11, you have to sum the values. And this is more difficult. Remember, they have difficulty learning addition. And I think this is the problem, the heart of the problem. What I notice is that I never get those divisibility by base -1 or base +1. Well, I saw it once in thousands of examples, so it almost never happens. So this seems to be a hard task, but not learning, divisibility by powers of the base.
The token are just the digits.
The
token are just
the
digits separately.
Yes. And the thing is that when I say the token is the digits, I do this for you, because I could rename all the tokens. 1 could be banana, 2 could be blue. The model doesn't know the meaning, but there's 1 token per digit.
But sometimes the token would be the 2 first digits.
No, here is the digits in the base, in the representation base I have. So interestingly, for every, so I tried that in many bases for many models, and I can explain all the model prediction, 99.99 something, by 3 rules. There are 3 rules that apply all the time when the model learns the GCD and actually apply throughout training. So the prediction I call them deterministic. The model predicts a unique value f of k for almost all pairs of integers with GCD_k. So if you have AB with GCD_k, CD with GCD_k, the model predicts a function of k. And this is always true. The correct predictions are the products of prime dividing b. Actually, the products of small powers of prime dividing b. The small powers mean the number of digit of rightmost digit you need to attend to. Okay, and f of k, when the model is wrong, is the largest correct prediction that divides k. So, does the model learn the GCD? It doesn't. But what's interesting is that I can explain very precisely everything that the model does just by looking at the predictions. So the model are very explainable, and they sort of do correct math. They learn divisibility, they learn easy divisibility. So what happens? So of course you know how you could get very good results. You need to have high composite base. So like base 420. Yeah, divisible by a lot of numbers. And if you look at the performance, you can see that the performance can be high because there are so many GCD1, GCD2, small GCD that are easy to learn. But if you look at the number of correct GCD that the model predicts from 1 to 100, the model predicts only a handful. So for 6, it predicts 19 correct GCD. The best you can do is for base 10, where it predicts 38 GCD out of the 400 first, the number that are divisible by 3, by 2, by 3, by 4, by 9, by etc. Okay, so yeah, this is sort of disappointing. But in this table, there is something that is very curious. It's base 1000, because base 1000 should be like base 10. We should learn only 13 GCD. But much to my surprise, here you learn 22 GCD. You learn more GCD than you're supposed to by my 3 rules. So something is happening for the large bases. So in base 1000, after 25 million examples, so if you give a normal number of examples, the model is going to predict 13 GCDs, which are the products of small powers of 2 and small powers of 5. So, and in products of 1, 2, 4, 8 by 1, 5, 25 is correctly predicted, and all the rest is not predicted. You got the 3 rules. But if you wait, if you forget the machine during the weekend and come back, and you wait for 66 million examples, which is a lot, but not hugely enough. It's 1 more night or 2 more nights on those kind of models. All of a sudden, you have the products 1, 2, 4, 8, 16, 1, 5, 25, and you have 3. GCD3 has been learned, even though it's not a divisor of the base. So it might be using what you say. Actually, it doesn't. But a new GCD is being learned here. And this is very surprising because I tried, a larger base. So that was done last year. So the base is 2023. Sorry.
Why can you say that it doesn't?
Oh, because I'm going to show you why. Just a few minutes. So I took base 2023. It was done last year. So 2023 is 9. It's 7 times 17 square. So if you train the model, you expect that the model is going to learn 1, 7, and 17, maybe 49, but that's all it can learn. And actually, that's what happens. So on the right here, you get the train loss, what you minimize, and you get the number of GCD predicted. And you see the 3 curves which correspond to 3 models with different initialization. After, say, a few epochs, and until 100 epochs, they learn 3 GCD, which is 1, 17, and 7 and 17, which is what I expect. But the funny thing happens after, about 30 million examples or more. At one moment, the loss is flat. So it looks like the model has no signal, but all of a sudden the loss drops. And the accuracy, the model all of a sudden learns 3 new GCD. And now it predicts correctly 6 GCDs. And if you look at the GCDs it predicts in base 2023, the new divisor is 3. It learns 3. And when it learns 3, it learns to predict 3, but also 21 and also 51. So the products by 3 of 7 and 17. And then it stops for a long time. And after, again, 30 million examples, 2 is learned. And again, the products, 2, 6, 14, 34, 42. And you get to 12 GCD or 11 GCD. And then after a while, you learn 4 and the products, etc. So if you have a large base and you train for a very long time, something happens. So I call it grokking, but it's not exactly the grokking you have in the literature. What happens is that all of a sudden, you know, the model seems not to be learning, but something must be happening under the hood. And all of a sudden, the model learns a new small primes. The primes are learned more or less in order, not quite. You see 3 is learned before 2. But the small primes end up being learned, and the model knows new GCD this way. And it's very curious because learning happens suddenly. You know, there's a drop. All the multiples are learned at the same time. And the funny thing is that if you look at the model prediction, the 3 rules apply exactly the same. You still have, you know, a unique prediction for the GCD, and the prediction is always the largest divisor, etc. It's just that you know a few more divisors than the obvious divisors of the number. So this is quite surprising. So this is the 3 rules, and you know, you can see that for any large base. So these are, you know, a lot of base I tried. This is the GCDs predicted, the divisor predicted, which are correct. And you can see the non-divisors that were predicted, and every time the number behind is the epoch, so the number of time. Yeah.
Do these additional big numbers that you learn correspond to the ones where you have the
No.
expansion
No.
that has a small period?
No, it's not. For instance, b minus 1, b plus 1 is not learned. You know, b minus 1, b plus 1, usually it's easy, it's like 9 and 11. And it's not, no. If you look at the ones that are learned, they are the small values. So you usually learn 2 first, followed by 3, or 3 followed by 2, if it's not a divisor of the base. So what the model seems to learn after a long time is the prime and small powers of prime roughly in order. And you see this, for instance, if you take the base 2017, which happens to be a prime, the model for a long time only predicts everything as 1. And all of a sudden, it predicts 2 and then 3, and they are not special in 2017. And you get that for the others as well. So this is very curious, because when you think of it, we have an algorithm. You know, if this pattern continues, if I send enough, it's not efficient, of course. But the model is learning the divisors one after the other and applying the 3 rules. So it's not learning Euclid, but it's learning kind of a sieve algorithm. You know, when you learn the small divisors, yep. Well, actually, it learns primes here, because it learns 2, 3, 5, and the small powers of primes.
But could you adapt something like that to really learn primes?
To learn all the primes? Well, the problem with the primes is the distribution, because you would need to have very large numbers to, you know, the problem is that if you want to train a model to know if a number is prime or not prime, you will have a lot of trouble having the model say that everything is composite. Or just testing divisibility by 2 or 3 and 5 because it's so easy. So
another question, because you said, well, you go from 10 to 1,000, and suddenly 1,000 works better than 10.
Yeah.
But if you now learn also basically the conversion between base 10 and base 1,000, which is very easy to learn.
Yeah.
What happens?
So this I don't know. What I tried is that I really tried to get small bases, and it seems to be difficult to learn, you know, to get the grokking to happen for small base. So what I observe is that when the bases are very small and the sequences are long, the model seems to have difficulty. What I suspect is that when your sequences are long, the model is fixated on looking at the last tokens, because, you know, you have long sequence and all that. If the base is large, looking at the last token doesn't matter because you only have 2 tokens or something like that. And I suspect this is what helps the grokking happen. If you learn an additional thing like a mapping, I would expect you would end up learning the divisibility like 1,000. It would be very hard to know whether it's known because it has learned 1,000 or whether it transferred 1,000 to 10. So I don't know how to make this into an experiment somehow. But I could think of it. So yeah, so you have a method here. You learn the divisibility, you learn the divisibility rules and use the divisibility to classify the operands. It's very easy to learn the divisibility by divisors of the base. And then you learn slowly the divisibility by other powers of primes. Okay? One very funny thing is that the learning happens in batches. You don't learn GCD one at a time. Every time you learn, say, 3 GCD, the next time you learn a prime, you learn 3 more. So all the classes of prediction double every time. And this is something, you know, that is a bit surprising. It's a bit like a phase transition or something like that in the latent space. Okay, so, and the algorithm is correct. It's very inefficient, but if I could learn, you know, all the GCDs this way, if I had enough time to train on so many things, I would end up with the correct GCD. You know, I get the correct GCD once I learn all the primes, all the powers of prime that divide my GCD. So the question is, okay, this is not a serious algorithm. You cannot do anything with that because we need a lot of examples. So could we improve? Could we make this much faster? So I'm going to show you 3 methods to accelerate this. The first method is that we train from individual examples. In my original thing, I generate example randomly, and since I have 10 to the 12 possible different examples, most of the examples the model sees during training are different. But that's not the way we learn. You know, we learn from repetition. So what would happen if I had repeated example in my training set? So this is blasphemy. You never do that in machine learning, but let's try that. The second one, you know, I've been talking about magical distribution, so why not change the distribution of input, the training distribution? And there are 2 ways to do that. You could change the distribution of operands, so A and B, and the distribution of outcomes. We know that 1s are more common than 2, than 4, etc. So the first thing is a paper we published this summer, and this is an example. So the first example was on the GCD. So this is a GCD in Bayes 1000. I'm training on integers. That's the same method, you know, integers between 1 and 1,000,000, and I'm calculating the GCD. The thing is that I'm going to train for a long period of time, and this is what you see here. So here, that's the total number of training examples that the model sees. Here you have 1 billion examples during training. And the different groups is that I'm training from a fixed training set. So in one case, in the first curve, the blue curve, I only have 1,000,000 examples, and I repeat them. Randomly, but I repeat them. In the second one, I have 5 million, 10 million. And the last one, the pink one, I have, you know, it's the original experiment, and I have infinite data, as much data as I want. So I'm training to do the GCD, and you see the first column here. You can see that all the models, I only have 30 million examples. And all my model learn 13 GCD, which are the divisors of 10. We've seen that, or 1,000, we've seen that before. But 2 models do better, they're close to 20. And they happen to be the models with less examples, the models with repeated examples. If I go to 150 million, you can see that the blue model, which has only 1 million examples, sort of saturates. It overfits. It doesn't have enough data to learn more. But the 5 million, the model with 5 million examples, now repeated a lot. They're repeated 30 times on average, goes to 35 GCD. And you can see that the best models are the models that are repeated, not the model with infinite data. And this happened throughout the curve. You can see at 1 billion example, which is really a lot. You can see that the infinite model, the model that has non-repeated data, learns about 23, 24 GCD, which is what I observed before. But the model trained on 25 million or 50 million data learns almost 60. So this is the average of several models. So the best model did better than that, but that's not really important. So this is an interesting intuition. It's a bit unnatural, but it shows that if you repeat examples, this is going to, so if you repeat examples, this is going to help the model learn. You don't want to repeat too much. If you repeat too much, the model memorizes the examples, you have overfitting, and it doesn't work. But if you repeat enough, there's kind of a trade-off that seems to be to help the model learn. So there's a virtue of repetition here. So you can push this forward. The idea is that you know that repetition helps, but too much repetition causes overfit. So the idea is that suppose you have 100 million examples, and that's all you have. There's a wise way to use them. You could select, say, 50K examples that you're going to repeat, and the rest you don't repeat. You've got the best of both worlds, right? You got repeated examples that will help the model, but you got diverse examples that are not repeated that prevent overfit. So you see what happens here. The right curves are the curves with, you know, everything is repeated the same, and the other one are the 2 sample example. And you can see that it doesn't learn, it learns a little better, but only marginally better. But the funny thing is that it learns much faster. So here you see the virtue of repetition. If you do that in base 1000, you remember base 1000, I could do 20, 23, 22, 23 different GCDs. Using just this repetition trick, the model is going to learn like 72 GCDs. So my GCDs are way better learned just by having examples that are seen several times. Okay? So it seems to be just an effect of repetition. Because when I saw that, I said, okay, maybe the repeated examples are special, but I took them randomly. So I said, but what happens if I select specific examples, if I select easier examples, or more diverse examples, or special examples, you know, few primes, large primes, whatever. It doesn't improve, it doesn't degrade performance, but it doesn't improve. So it's really an effect of repetition. And also, if you want to train first on the repeated and then on the non-repeated, it doesn't work. It breaks everything. You need to mix the repeated and non-repeated example, even if at the training batches, or the effect disappears. But you have something that works, and we've reproduced it. We're using it in crypto and had great results with that just by, you know, having less data and repeating it, which is a good thing if you have to generate the data. So it's something that seems to work, and you can improve the result, you know, going from 25 to 72 GCD this way. Another way you could improve the calculation of the GCD is an argument about the training distribution. So you remember my operands are uniformly distributed. The A and B are uniformly distributed between 1 and a million, which means that 90% of the operands that the model sees are larger than 100,000, which means that the small values of the GCD are never seen during training, or almost never seen. This is absolutely not the way we learn. We learn from small examples and generalize to large. And when you rote learn sometime, you know, remember multiplication tables. When you learn the multiplication tables, you can learn larger multiplication much easier. So the idea here is say, okay, let's change the operand distribution. Instead of sampling A and B randomly, uniformly, I could do them log uniformly. So say that the probability of sampling A is C on A. Okay, so basically I do a log and calculate the log of the thing. So the funny thing in that case, everything I'm doing is out of distribution. I'm testing on a regular distribution of GCD. So I'm not training on the distribution I use for testing. This again is blasphemy. You know, you're not supposed to do that because it should degrade, remember yesterday, it should degrade your results. But the big surprise is that if you do that, you have an improvement. So the curve become a bit noisy, and you can see that the steps are getting, so some noise is being introduced by this method. But the performance is much higher. You see for base 10, if you have a uniform distribution of operand, you can learn 13 GCD, 13 different GCDs. If you have a log uniform, you can learn 48. And same goes for base 1000, you go from 22 to 71, which is pretty much the same distribution as the repeated examples. To be honest, I suspect that the two phenomena are linked, you know, because if you have many small examples, then those small examples are repeated somehow. They're not exactly repeated exactly the same way as you would do, but they're probably linked. One thing I noticed is that if I mix the two, I don't get any improvement. It's one or the other. So both bring something, but they don't bring better. Yeah?
Again, what do you repeat examples?
So the repeat examples, you build a training set of 50 million examples, and then you select randomly in this sample. So the idea is that, you know, you instead of rolling a new pair of AB every time, you select one pair of AB out of 50 million, but not repeat them in order. You don't want to, you don't want to have this kind of, you know, this could create, I'm not sure it would happen, but you really don't want to have this kind of effect that would come from the fact that all the numbers are seen in the same order or something. Yeah.
What about sampling on the result rather than on the operand?
That's a good question. That's the next slide. So if you look at the distribution of operands, you can see that you get an improvement, you know, everywhere. You get an improvement for the small base and for the large bases. So this is, and you get, you know, the best values you get are about 70 GCD. So you can predict 70 GCD out of the first 100. So it's not perfect, but it's much, much better, and it's faster. So yeah, the next idea is the distribution of outcomes, because there are so many ones, and less 2, and less 3, and less 4. So it means that the large GCD that I would like to learn are very difficult to learn because I never see them during training. So I might want to change. So I know that the GCDs are 1 on k square. So, since I was doing log uniform, let's do 1 on k. And you might wonder, uniform, I'm coming to that in a while. But if I do 1 on k, so the funny thing is that if I have uniform and 1 on k, you can see those are the 2 columns, there's a small improvement, but a small improvement. What really makes it is that if you have log uniform operands and 1 on k, and then you can reach almost 90% accuracy, 91% accuracy. Even better is the mixture of repeated examples and log uniform outcomes, and then you predict 99 GCD of 100, so you always predict the GCD with that. So this is the way you can predict the GCD, the sum of those two things. Okay? So what I'm saying here, what we've seen is that you have a model that predicts, you can interpret the predictions, and then you have a battery of tricks, repeated examples, changing the training distribution that allow you to improve up to a point where you manage to learn the GCD almost perfectly. So you need large base, you need repeated examples, you need to correct the outcome distribution. But can transformer learn the GCD? The answer is yes. It takes some work and it's specific to a problem, but you can do that. Okay, so this is what I said. Okay, so at this point, you might say, okay, the outcomes. You change them from 1 on k square to 1 on k, but why not uniform outcomes? Why not balance the results? So have as many ones as 2, as 3, as 4. So I tried that, it was so obvious. And then you get those results, which are very, very strange. So if you look at the loss, what the model learns on that, the loss is flat. So it looks like the model learns nothing. If you look at the accuracy, it varies totally randomly. So sometimes the model learns very well, and this cannot happen by chance. So sometimes it can predict, almost all GCD or something like that. And sometimes it goes down and it totally fails. The next epoch it will fail, etc. And if you look at the correct GCD, they still have the shape structure, the step structure, and the number of GCD is roughly correct. So something totally wonky is happening there. It seems that the model is learning something because I wouldn't have this curve. It seems to be totally, well, there's a large randomness happening here, and the loss is of no help. So what is really happening? So as usual, I'm going to look at the model predictions. So I'm in base 10 here. Why base 10? Because it's easier. So I'm in base 10, and you remember in base 10 the model predicts 13 GCD, and they predict classes. So you have the blue class, the class A, which is 1, 3, 7, 9, 11, 13, 17, 19. They're all predicted as 1. The second class, 2, 6, 14, 18 are predicted as 2. The third class, 4, 12, etc. are predicted as 4, and the next class is predicted as 5, etc. Now here, I show you the predictions of the model for all the elements in this class for 5 consecutive epochs. So I stop the model, at different moments in training, and I show what happens. So you can see at epochs 2, 6, 6, chosen randomly, you can see that all the class A is predicted as 1, so it's correctly predicted. All the class B is predicted as 2 and correctly predicted. Class C is predicted as 44, it should be 4, so it's wrong. Class 5 is predicted as 5, so correctly predicted. So the model is pretty good there. You wait for the next one, and you see class 1 is all predicted the same, but 19 now, so it's a different prediction. And then the next one, it's 73, and 7, and 13. So what seems to happen is that at every epoch, the model learns the same classes. The blue class are always predicted the same. So it knows how to classify the entries, but it doesn't know how to predict the correct value of the entries. It predicts randomly a value, which sometimes is the correct one, sometimes a different one. So what seems to be happening here is that when predicting the GCD, my model is actually doing 2 things. It's classifying its entries in A-B pairs into groups, and saying this group, has a certain value f of k. There's a certain value predicted there. But then it needs to find the value, the predicted value for that. And what we're going to see that again. What happens is that if you use, if you have you know, if you have not uniform distribution, the most common values in class 1 is 1. The most common value in class B is 2. The most common value, because the GCDs are ordered. If you make everything uniform, then what's the most common prediction? Well, it depends on the randomness of how you select things, and this is how this happens. So this is an interesting learning because it tells us something on the way the model is learning. The model is doing two things. It's learning to classify its entries, and then it's learning to predict from these entries. And the prediction depends on the frequency of the labels of these entries. Yeah. So, finishing on the transformers, on the GCD. So what's happening when I learn the GCD? I can learn the GCD. What the model is doing is that they seem to be classifying their input according to the common divisors that they share. Okay, so you got classes for guys who share 1, guys who share 2, guys who share 4, etc. And the divisors you know are to start with 1 and the products of divisors of the base. And then, as the model learns, powers of prime more or less in order. When a new divisor is learned, all the class split into 2. You know, 1, when you learn 3, 1 splits in 1, 3. 7 split in 7, 21. So the class is, you know, it's like a new dimension appearing. It's meiosis, if you like, or something like that. And the GCD, therefore, are learned in batches. What's interesting is that the model prediction for each class is not the same process. It depends on the frequency of the labels. And we're going to see a very compelling example of why this happens now. So I got, 10 minutes, that's fine. I'm going to show you very quickly what we can do with modular arithmetic, which is basically it's a way to show that what we saw on the GCD is not specific to the GCD. It would extend to other things. So are the results specific to GCD? I want to look modular arithmetic, so A plus B modulo P, or A times B modulo P, A, B between 1 and a million, just like the GCD, and P being 67 or something like that. This is useful. Cryptography, many things are full of that. So it's not just for the fun of it. This is really an interesting application. So I tried for modular addition all the values of P. I tried composite and prime numbers from 64 to 73. Again, I got 10 to the 12 possible outputs, so no memorization, etc. I have 21 models, and I trained them on 600 million examples. And what I noticed is that if I train, you know, on random examples, etc., my model exactly predict 100 on P% of test example. So they predict one single value. And so one out of P value is correctly predicted because the model makes the same prediction for everyone, but the model doesn't learn modular addition. The funny thing is that the unique prediction changes from one epoch to the next because, you know, they're all equiprobable. So the same thing that happened with my GCD happens again there. Okay? So what happens if you just train modular addition? The model doesn't learn. It predicts, you know, one single value, which is randomly selected as the value that is seen most often so far. And this changes over time. But the model doesn't learn modular addition. It's too hard for it. Now, just a fun thing. I'm saying I'm predicting the most common value. Well, I could actually bias the outcome distribution. You know, I could have a small additional percentage of pairs that sum to 0, or 1, or 2, or 3, or 4. Okay? So basically, I'm changing a little my training distribution by making one outcome a little more common than the rest. So for P equals 64, I have outcome 0 to 4 with probability 175%, and all the other with probability 155. So I cheated a little on my training distribution. When I do this, the model now predicts from one epoch to the next, but it only predicts 0, 1, 2, 3, 4. So this sort of proved my point that it's the most common prediction. The model will predict the most common of the label in each class, in this case, in the unit class. Okay, so it looks like modular addition is more difficult than GCD. I cannot learn it. Can I do better than that? Yes, I could do repeated examples. So I'm going to try the same tricks. If I do repeated examples, you can see that the percentage sometimes are better. So these are the learning curves, and you see that the steps are larger than just 1%. So for P equals 67, 71, 73 primes, I'm just learning 1 to 4 to 1, so there's only one class predicted. If p equals 66, I got 2 classes. 65, 5 classes, 72, 64, I got 8 classes. So the model is learning the modulo. Basically, it's learning 2 classes, the odd values or the even values. When it learns 8 classes, it's mod 1, mod 0, mod 1, mod 2, it's mod 8. And those values, 2, 5, and 8, correspond again to the GCD of the divisors of the base. So a similar phenomenon happens here. I'm still not learning addition, but instead of learning just one value, the model has sort of learned a modular element related to the base of representation in that case. Okay, but the model is still not learning. Repeated examples don't help learn the GCD. Okay, so if I oversample, I get the same kind of result, etc. So can you do better with the log uniform operands? So actually, yes, if you train p equals 67 with log uniform operands, you can see curves that go up to 100%. So if you change the distribution of operands, you can manage to learn modular addition. Unfortunately, you can see the learning curve. This is the accuracy on the test set, and you can see it varies very widely. So on average, it goes up, but from one epoch to the next, it might fail. And this is strange, my test set is very large, so I got the statistics with me. It's not a randomization problem. It's really something with the model. And one way you can interpret it is, just as before, you could look at the correct predictions and what the model predicts. So here you can see, p equals 65, and I'm looking, if the correct value is 0, I'm looking at the model prediction. And you can see that when the correct value is 0, the model tends to predict sometimes 0, but sometimes it's split between 0, 64, and 1. So the model is doing, it's not trained this way, it does cross entropy, but the model is looking like it's learning, it's been learning a least square, a distance to the thing. And you can see that, and so you can see the values changing because I'm only testing if you get the right value, but if you one off or one wrong, one off up or down, the model will do worse. But you see in this case, if you have modular addition and log uniform example, you end up learning, but you're absolutely not learning the same system as in. So the distribution helps, but it doesn't help in the same way as it helped with the GCD. And this is, sort of surprising. Yeah, so that's what I had on modular addition. I'd like to finish very quickly on modular multiplication. So what you see on modular addition is that, it's a harder task than the GCD. This was not a given, but I observed that. What you see is that you can do a little better if you use repeated data, but you still don't learn it. But the log uniform operand look like one of those magical distributions that are robust everywhere, because if you have those, you learn better, even though it is noisy. But the patterns of learning are different. In one case, you learn kind of a distance between numbers. In the other case, you don't. So the next idea is what happens if I learn modular multiplication modulo 67. And here I suppose you know that there's an isomorphism between multiplication mod 67 and addition mod 66. So I'm not expecting multiplication to be very different from addition, right? It should be pretty much the same. You have a 0, which is more common, and all the rest behave exactly as an addition modulo 66. That's just the exponential and logarithm, basically. So I'm expecting the model to quickly learn the 0 class because it's more frequent, and then to have pretty much the same performance as the multiplication. So this was addition modulo 66. So what I'm expecting to have, infinite data, so nothing is learned. This is what you get with repeated examples. So you basically learn 3 elements, which are the parity modulo 2, okay, because 66 is divisible by 2, which is the smallest division. And here, what you expect to see with log uniform operands, so it's very noisy, but you end up learning. But it doesn't happen. So the funny thing is that with unlimited data, there's no surprise. The model, everything is predicted as 0. You get 3% accuracy. The model doesn't learn. No surprise. Multiplication is just as hard as addition. But if you have repeated examples, you see something like this. So these are many different models that have learned for a long period of time. And you see that the values have steps. It's extremely quantized. You know, there are only a certain number of values that are possible, which happen to be multiple, well, 1 plus the divisor of 66. So number that are not prime, co-prime with 66. So it's interesting because there's a number theory thing hidden here. I don't know what, but there's something happening. But the funny thing is that some of the models learn 100%, whereas the addition didn't work. So it's funny because you have two operations that are totally isomorphic, and we can prove that. But actually on those data, one learns and one doesn't learn. So something different is happening here, which this is work in progress. I still don't understand, but something happens.
So how do you represent the numbers from?
Exactly as before. You know, it's in here I'm in base 1000, so they're just sequence of digits. Exactly as in the GCD and the addition and all that. There's no difference. And finally, I'd like to show, the log uniforms. And the log uniforms, I don't have the noisy curve, or it's very not noisy. The model starts learning, 0, and all at once it learns 100%. So on the module multiplication, you see that the log uniform distribution is really magic. It works very, very well. You learn everything. So this operation that was impossible to learn without it is learnable with repeated example, but even more with log uniform operands. And again, you can see that multiplication doesn't behave as addition, even though they are supposed, theory says they should be the same. So something curious is happening here. Okay, so yeah, I'll stay with the temporary conclusions. So the main conclusion here is that you can learn arithmetic with those models, but you need to work for it. Learning seems to happen in two stages. You have that clustering of the input, and then you select the most common label to predict each group. So the distribution of outcomes is important. You need to have a biased, decreasing distribution of outcome for the GCD, for instance, or you will have the correct classes, but you won't be able to predict them. Training distribution matter. They matter much more than architecture, and this is yet a non-studied, there's very little study on this, but this seems to be very important. And there seem to be some of those magical distributions, like the one I had for the eigenvalues. Log uniform operands seem to be really an important trick. Okay, and outcome distribution may matter, but it doesn't matter for modular arithmetic because everything is equiprobable. Yeah, so I'd like to finish with a couple of questions for the mathematicians here, if you want to work on this. So I have 3 questions here. One question is, what happens with the prediction classes? You have this pattern where the model begins putting all the input into one big class. And all of a sudden, the class splits in 2. And then the class splits in 4 or 5 or something. So you have those kinds of phase transition. This must be a property of the dynamic. This must be a property of the way the gradient, the model learns. So could we have a mathematical model for that? Could we try to think of it as, a change of rank in the representation space, in the latent space? Something is happening here. A second thing is the training and test distribution. This is obvious. It's very important to have good training and test distribution, but we don't even have a theory. What's the distribution of problems? We don't know. We don't have a measure on problems, so we need to define that. And we seem to have better distribution on others, and even distribution that seem to be universally better. So this, I think, is a mathematical or a statistical problem, and it's something that should be addressed. The last thing is about repeated examples. Because you see, when I repeat my examples, my model don't see examples. It's not like us rote learning. The model is seeing examples 20 times in a row, and you're seeing the multiplication tables and stuff like that. It's not like that. When the model sees a repeated example, it sees the repeated examples every 1,000,000 examples or every 2 million examples. And it matters. I observe effect. So how does the model do that? How does the model manage, every once in a while say, oh, 3 million examples ago I've seen that guy, that exact guy. And it has to be the exact same. So there's something, it's exactly déjà vu or jamais vu. The model has a way to tell that I've seen this example, I've not seen it. And it matters because you learn differently. This seems to be a very important thing. So that's a question that needs to be addressed at some point. So yeah, I had all the slides on collapse, but I don't have the time, so another time. Thank you very much.
Thank you. So thank you very much. So, questions for François?
Yes, about this grokking moment, the understanding moment of the apprentissage. There is this phase transition, which is occurring when you have a step by step. But is it the case, or is there are there some non-examples of some kind of meta phase transitions where suddenly he's learning much more than one by one?
So that's what you saw here. You see all the class splitting. So you learn 3 GCD at a time. And you have cases, so there's one case which is interesting, and you had the same, which is this one. So you see here, this is multiplication modulo 67 with the log uniform operand. So you can see here the model easily learned 3%, which is predicting everything at 0. And then it's flat for a while, and then all of a sudden it goes to 100%. So you have a case where the phase transition happens in just one time. You have case where it happened in 2 or 3 times. You can see this here. So if you look at the curves, you know you learn 1, then 3, and then, whoop, 50, and then 100.
Yes, but there are always, let's say, similar.
Yes.
So my question was, after learning more and more cases like this, is there something which is much faster?
So this I don't know. This I don't know. It seems so, because you could say that this is what we saw in the GCD. If you have repeated example, you got the same grokking pattern, but it happens faster. And if you have log uniform outcomes, it's the same, but it happens faster. So I think the point could be made that what repeated example or what distribution do is that they accelerate the training, and they make the same learning to happen faster. But this would need to be more studied. I mean, it's only 2 or 3 examples here.
So it's another question about phase transitions. So if I remember well, you described attention as a graph of weights on the positions in.
Yes.
So is this a good candidate to observe another phase transition?
So I don't really know. If you look at the attention patterns, they're always very nice to look at, but they're always very difficult to interpret. So I'm not sure it happens in the attention mechanism. My feeling. So far we did some research on that in the cryptography paper, because when you do cryptography, the phase transition is the moment the model knows the secret. So this is the moment you want to stop and open the model and pry away the secret from the model. So this is an important moment. And one thing we have noticed that the grokking people have noticed in their case is that at the time the phase transition happened, there is a little change, not in the weights, but in the values of the gradients. The gradients have a little more variance, so the gradient become larger. It might be just after or just before but there seem to be things happening in the learning process. I know some people have wanted to look at the Hessians, so the derivatives of the gradient, to see if something happened. So there have been studies on grokking, but grokking is a slightly different thing, but it would seem that the transition could be detected or planned by looking at, basically it's not the loss, because the loss is flat and drops. So it has to be something, it has to be linked to the loss, because this is only information that gets into the model. But that brutal change is probably a moment where, the gradient abruptly changes. So you could probably detect it. What's interesting is that you want to detect it, but once you understand how it happened, what you would like to build ultimately are architectures that facilitate this. So you would like to change the architecture. Once you understand the pattern, you can try to change the architecture. What I'm saying is that I'm not absolutely sure this is linked to the transformer. So 2 reasons for that. The first thing is that everything I show here are transformers. But when you write papers, you always get reviewer 2 that ask you for, does it work in other architectures? And all the things I show you here work in LSTM, work in GRU, so in the previous models. As for grokking, people say, grokking is a thing of transformer, and people start talking, until there was a paper a couple of years ago by Andrei Gromov, who showed grokking in basic multi-layer perceptron, so basic numbers. So it seems that, I'm not sure it's because of the attention, because I think you can observe that in different models. But again, this would need to be studied more.
So yeah, I'm not sure about transformers. So the architecture, they have many layers, and you didn't speak about how does it help to increase the number of layers, or what is the dependency on learning with respect to the number of layers?
Yeah. So you have two dependencies. One dependency, so you have three parameters basically in transformers. You have the number of layers, and everything increases linearly. You have the dimension of the internal representation, and this moves as a square of the number of parameters. And then you have the number of attention heads. One thing I've been noticing is that the attention heads usually don't matter. You need enough of them, but that doesn't matter. One thing I've been noticing is that in general, the dimension, the broad dimensional mass transformer is more important than the layers. So you don't need to have very deep model, you need to have broad model. You need to have, so usually when you don't learn, you want a broader model. So the impact of having more parameters, so broader, deeper, maybe both, is usually in math you can attack larger problem. You can attack larger matrices, you will need larger model. That's obvious. Usually if your model starts overfitting, having more parameters will prevent the overfitting. This is very, this is not obvious, but this happens all the time. So more parameter prevents the model from memorizing, because it has slack, if you like. And more parameters will usually cause the model to learn a bit faster. Not extremely, not too many, but usually the models with more parameters, so this will be offset by the fact that the gradient takes more time to flow in a larger model. But if you look at the number of examples needed, usually more parameters help learn better. One thing I observe in math, on the other hand, is that if I try to reduce the number of parameters, and especially the depth, I can usually go with very small depth. So all those papers are done with transform with 4 layers. But I could do 2 layers. And this is sort of heresy in large language model. They want very deep things, etc. And many people say, oh, but if you have only 2 layers, the number of things you can do, the size of the loops or whatever is limited. But I think this is not the case. I think because the combination of high dimension plus the attention allows the model to learn very complex algorithm in just a few layers. 1 layer is usually not enough, but 2 or 4 layers is usually enough. So I tend to use small number of layers because it usually works, unless I want to have larger mathematical objects like 12 matrices. Yeah, you need deeper and larger models.
So yeah, so you would so you would expect that with more parameters you would start to overfit at some point, but that's not what happens with transformers and deep learning models. I'm aware of, there's probably many papers on the subject, but I'm aware of one strand of research which is called singular learning theory, which seems to be a generalization of Bayesian learning theory that kind of tries to take into account the full geometry of your model, especially things that they call singular points. And by singular points, what they just mean is that if you consider the relative information, the Kullback-Leibler distance, from the distribution implemented by the model and the truth, it's not hard to see that there are many weights that implement the same, many sets of weights that implement the same distribution. And so in particular, you could have many sets of weights that implement a distribution which has distance 0 to the true distribution. And so if you think of the Kullback-Leibler distance, if you look at its 0 set, this 0 set will not necessarily be a point, but it will be some general set, subset of the weights, and this is what they call the singular set. And so I think there have been attempts to use this to predict phase transitions, and they use a different quantity which is associated to singularities.
Yeah.
So my question is, Yeah, have you heard of this?
No, I haven't read that.
Okay.
I haven't read that. In general, I'm sort of prudent with mechanistic interpretability, trying to understand the weights. I like to understand the prediction. That's what I do in the GCD. I try to understand the representation, the latent space. The weights, there are so many weights. It's so complicated, and if you have a larger transformer, you have even more weights, that I have the feeling that it's sort of a rabbit hole. It takes a lot of time. So I have a lot of respect for the people who do this because I think it's very interesting. But in the case of mathematics, I suspect that actually looking at the latent space is a cheaper way to understand what the model is doing. Yeah, that's more my personal take on this. There's really a lot of people that do this mechanistic, weight interpretation, and yes, you learn a lot of things this way.
Okay. And we have one last question. A question. So, can we learn how to approximate a function like the GCD for a given model? What's the best way to approximate a function?
So,
how it depends on the model you choose.
So with the yeah.
Maybe you can take polynomials.
So with the transformer, what I see on GCD, for instance, is that the architecture doesn't matter that much. The training distribution matters, the representation, tokenization matters. The architecture matters less. There have been other people who have been trying to learn other arithmetic function. Recently there was, I don't know if it was a paper, but there was at least a conference by Jordan Ellenberg, combinatorist, who was trying to learn the Möbius function, which is a number theoretic function. And he suffered a lot. It's exactly the same point as with learning whether a number is prime, because the model was learning divisibility by 2, by 3, by 4, and doing everything this way and had a good approximation. So the main problem is that we know that that those models are universal approximators. So in theory, you could approximate any function you have, which was, I think, your point. But the difficulty is that given a given set of data, if you think of it as a minimization problem, inside some kind of space, there are very, very deep local minima that sometimes are difficult to get. So I think the real problem is not, can you approximate a function? Because yes, you can. Is what distribution do you need to be able to approximate correctly a function with gradients, with gradient minimization? And there are examples, let's say some functions, for instance, parity is known to be very, very hard to learn. Anything in characteristic 2 basically is difficult to learn because the gradient doesn't help. You can fall on a torus of size 1. If you're at the top, all directions are the same. So the gradient is difficult to use there. But practically, yeah, I think it's less the problem. So can you learn any function, any real function, any arithmetic function? I'm sure you can. But the practical question is, how do you learn it? Which example do you use?
Thank you.
Thank you again.